That was when I had to, so I couldn't.
We'll go down after.
You gonna do what?
All right, everybody, it is 10 o'clock. It's great to see all of you. I'm glad you're here. Thanks for bearing with me last week while I was out of town. I hope that worked okay to take some notes on Zoom and all of that. It's not always ideal, but I've gotten better at it. You should have seen me when I was first doing that at the start of COVID. I didn't realize that the cold air in that garage I teach in was keeping me from erasing the board. So I figured that out. I don't know if you realized that I had a heater going in that room last Thursday just to keep that board warm so I could erase it. But anyway, I hope it worked out okay. We're going to have some time today to kind of review what was in that lecture a little bit, which I think will be helpful. Don't forget that there is a homework assignment due tonight. It's on this annihilator topic that I went through last Thursday in the Zoom class. And if there's any questions you guys want to ask me about it, we can certainly do that. In a little while, I'll give you a chance to throw any problems up on the board that you might want me to try to give you some hints for. But anyway, I also have office hours after class, and I have office hours this evening, both in person and in Zoom. My office hours have been kind of quiet lately. I don't know if that's just because I was gone last week, or maybe the material's not so bad and people don't have a lot of questions. But anyway, I'm still around, still happy to help out as much as possible. We are going to finish chapter 8 today, which will be nice. So we'll be ready to move into chapter 9, which is the last chapter actually for the semester. So we're almost getting to the finish line. Only have like 5 more lectures left actually for the whole semester. It's scary how fast this is going by. But anyway, yeah, it's been great. Before I do my recap, one other quick comment. Sorry, I'm still clearing my throat from that, whatever I had 2 weeks ago. You should have gotten a notification to fill out an SOQ form for this class, and the department just bugs me like crazy about this, like constantly wanting me to get people to fill those out. Even though I've taught this class many, many times, I always feel like I can learn something each time I teach it. So if you guys have feedback for me, things that you liked about the class, write them down in that SOQ form for me so that I can keep doing them. Especially things like recording these videos, was that helpful? Or, do you like the structure of the homework and the extra credit quizzes and videos and stuff like that? Or should I change everything? If you have feedback for me, I would love to get that. If there's things you didn't like, I know you didn't like the exams probably, but if there's anything else that you didn't like that you think I could do better, I will always love to hear from you about that. So try to fill out those SOQ forms. You still have a couple of weeks to do that, but it does help me out. I do read every single comment that people put in there, and I take it to heart. So I really, really would appreciate that. Okay, I don't have any other announcements. Does anybody have any questions for me? Yes, Roman?
Is our next exam?
Yeah, the next exam is not the week when we come back from Thanksgiving, but the Tuesday of the week after that. I think it's on December 9th. So it's still a few weeks off because we have a holiday next week. Yeah, so everybody knows that, right? Next week we have no classes at all. When we come back from the break, I could be really diabolical and give you an exam right when we come back from the break, but I don't like to do that. I like to give people a little time to get back into their rhythm again. So we won't have an exam until the following Tuesday. Yeah, sure. Actually, that third midterm will only be about 1 week before our final. But studying for that third midterm is going to be so comprehensive already because the stuff in chapter 9 like uses everything from the whole semester pretty much. So you will be reviewing for the final kind of at the same time that you're getting ready for that midterm. I think it actually works out pretty nicely in that respect. So it's a good point. Okay, yes, Jakob.
So with that, like last week before the final, are we learning like new information? Or is it just
on Tuesday, we'll have the exam. So there won't be anything going on except the exam on Tuesday. On Thursday, there will be one last little 40-minute snippet I want to share with you guys that will be new. And then we'll spend the rest of that last class just kind of reviewing, putting it all together. Yeah. for sure. Okay, guys, on the board over here, my usual start off to the class, which is a recap of kind of the big highlights from the last lecture. And the big highlight really is this 3-step process. So if I have an nth order linear non-homogeneous differential equation, the non-homogeneous is referring to the fact that there's an f of x on the right-hand side. If we have that kind of a differential equation, we can try to solve it in 3 steps. Okay, so I've got them up here for you. The first step is to solve the corresponding homogeneous differential equation. That's where you just ignore capital F for the time being, and you just solve L of y equals 0. Okay, when you get the solution for that, we're going to call it the complementary function. That's standard terminology. And I'm going to denote it as y sub c of x. And I'm going to put a box around it every time I find that, because we're going to not want to lose track of that as we go through these 3 steps. Okay, so the first step is to just write down that complementary function. Awesome. Now, the second step is to find one particular solution, which I'm going to put in a box as well. It's called y sub p of x. And this is one particular solution to the original non-homogeneous equation. Remember, guys, every differential equation actually has infinitely many solutions, right? We only have to find one particular solution right now in step 2. Because what we're going to do is add step 2 back to step 1 to get the general solution, which is the third step, by the way, guys, is nothing but a quick write it down thing. You don't have to actually solve anything new. You're just piecing together the complementary function and the particular solution, right? To do the step 2 on Thursday in Zoom, I kind of went over this annihilator method with you. If you go to our Canvas page, I forgot, I was going to print out copies of this for you today, but I forgot to do that. There is a folder called Special Handouts, and one of the very first documents, let me just click into that. If we go into that Special Handouts folder, the very second document down is this annihilator and integrals table. So as I mentioned last time, guys, I will not make you memorize these annihilators. I'm going to give you this handout for your exams, and actually you might want to pull it up. Today we're going to do some group work, and you may even need to pull it up for that. You're certainly going to need it for the homework that's due tonight. So this is something to kind of bookmark and just be aware of, that this is there for you to use, just a table of annihilators. Okay, and the annihilators that we have, well, they involve trying to annihilate powers of x or exponential functions e to the ax or sines and cosines. That's mainly what we saw in our examples last time, or combinations of those, right? So you can have combinations of exponentials, sines and cosines, and powers of x. And all of those can be annihilated with this operator that involves d, the derivative operator d. Okay, anyway, no need to memorize any of that. We'll just take advantage of it. Are there any questions about sort of this is sort of the airplane view of the 3-step process from above, like what it looks like. Is everybody kind of feeling okay about that part of it at least? Then, of course, we have to get down in the trenches and do the 3 steps. So that's where the math comes in, the sort of the calculations and all of that. I thought we would warm up today with one example. I did 2 or 3 in our Zoom class last Thursday, but I'd like to do one that I can at least do live right in front of you directly here. So here it is. I'd like to solve this second order non-homogeneous differential equation. Y double prime minus 2y prime minus 3y equals 28 e to the 3x plus 5x squared. Okay, let's try and do our 3-step process. So for the solution, I'm just going to start here with step 1. And remember that in step 1, you ignore the right-hand side completely. So you're going to completely ignore the right-hand side of the differential equation, and you're simply going to focus on the left side. And I'm going to write the left side in the d notation, right? So the derivatives are represented with powers of d. So the second derivative would be d squared. and then minus 2 times the first derivative, which is d, and then minus 3, all of that of y equals 0. So when I'm doing the homogeneous differential equation, I just replace the right side with 0. Very, very simple process, guys, to now find my auxiliary equation. Do you remember how you find the auxiliary equation here? Adrian? Just turn the d's into r's, exactly. So this just becomes r squared minus 2r minus 3 equals 0. There's your auxiliary equation. And we've got to figure out the roots of this equation. This one is a quadratic equation. I'm never going to flinch if I see a quadratic equation because I can always use the quadratic formula. But actually, this one factors nicely. And so I'll do that for you really quickly here. It factors as r minus 3 times r plus 1. Okay, I think I did that right. And so my roots would be 3 and negative 1. What you'll notice is there's no repeated roots here, and there's also no complex roots here. So I don't have to deal with the x stacking thing that comes up when you have repeated roots. And I don't have to deal with sines or cosines that would come up if there were imaginary roots. So this is just a straight distinct real roots. I can go straight to the complementary function, right? And the way this would look is c1 times e to the 3x plus c2 times e to the negative x. And I am going to put that into a box so that I can find that later if I need to. So far, so good? So that goes by really quickly. All right, so let's start looking at step 2, if everybody's okay with the first part of the process there. Step 2 is where we have to find one particular solution to the original non-homogeneous equation. And for that, of course, I explained on Thursday the annihilator method. So we have to look at this right-hand side. This is the capital F right here. And I have to figure out what the annihilator of it would be. So this is denoted with A of D, as you'll recall. And remember that the 28 doesn't matter and the 5 doesn't matter. When you have constants involving these terms on the right-hand side, you can essentially just ignore them and focus on the actual functions of x that you have. Now, e to the 3x has an annihilator, and if we don't remember what it is, we can look it up in our table. It's actually number 2 in the table. E to the ax has an annihilator. I know it's probably a little hard to read from where you're sitting, but this is just d minus a. And we wrote that down last week. So d minus a, in this case, the a value is 3, so it's just d minus 3. Now, the 5x squared, again, I don't have to worry about the 5. I really just have to think about how to annihilate x squared. That comes from the first item in the table, or it just comes from you thinking about it. If I want to annihilate x squared using derivatives, all I have to do is take 3 derivatives. So that would be d cubed. What do I do with these 2 separate annihilators? Do I add them since this is added?
Oh, they're multiple.
No. Samantha, what do I do?
You
Multiply them. Yes, so my Zoom class was coming through decent enough for you guys to pick that up. If there are terms here that are added or subtracted, that's fine. But over on the annihilator side, you have to multiply those individual annihilators together. So this is what you would have. And of course, this is going to give you some quote unquote new roots. Remember that the roots that we get in step 1, I like to think of those as the old roots to the original auxiliary equation. But now, if we were to apply this annihilator to sort of both sides of our differential equation, we would pick up new roots. And the new roots are always just exactly lined up with the roots of this annihilator thing. I could turn these d's into r's again, or I can just look at it and write down what those r values are going to be. I can see that d minus 3 will give me a root of 3, and the d cubed gives me a root of 0 3 additional times. Okay, so those are my new roots. They are 3 along with 0, 0, and 0. Everybody with me? If you're good with that, we can go ahead and write down the form of the particular solution right now. Now, of course, this is going to consist of a bunch of terms that will have coefficients in front of them. As I mentioned on Thursday, I don't like to call the coefficients over here, C3, C4, and C5, because the coefficients in this particular solution have specific correct numerical values that we can actually find. And so I don't like to leave them arbitrary, because these are arbitrary right here. C1 and C2 are completely arbitrary, but the coefficients of this part will not be arbitrary. They will be with specific values you can solve for. So I don't like to call them C3, C4, and C5. Instead, you probably remember from last week that I called them A, B, C, whatever. You can use whatever notation you want, but I like to use A, B's, and C's. So let's get going with the first term. Now, I have a root of 3 here. So this term is going to be A times what? X times e to the 3x, right? I'm really glad that people put that x in there. That's because this root of 3 actually happens to be repeating one of the old roots. So this is not the first time that I'm seeing the root r equals 3. It's actually the second time. And remember that when the roots are repeating, we have to stack those x's. So I have an extra x here that I stacked because of the fact that the 3 is now a repeated root. Okay? So that looks good so far. And now for the next term, I go to the next root. The 0 that I see here, this really is the first time that I see 0. And so what would be the term that would go with that? Just b. Technically, it's b times e to the 0, but e to the 0 is just 1. So I don't have to write that down. And then what would be the next term?
CX.
CX, right? I'm stacking an x again because the 0 is repeated. And what would be the next term?
dx squared.
Dx squared, exactly. Sometimes people don't like to use d as one of their letters because, of course, we're using the d over here in the derivative notation. If this bothers you, you can always just skip to e. I like to just leave it as a d and just understand that this is a different d that we're talking about here. Now, guys, be sure to read the questions carefully, even on tonight's homework. There are some problems where, especially at the end of the assignment, where it just says, find the form of the particular solution. If they just ask you for that, you could put a box around this and call it good. And you wouldn't need to do anything else on step 2. Okay, in this case, guys, I would like to practice solving for these constants just one more time. This is actually the messiest part of it, is solving for A, B, C, and D right now. Because in order to do that, I actually have to take this whole gadget and plug it back into my left side of my differential equation. And that means I need to take 2 derivatives of it. By the way, the number of derivatives that you have to take is always just whatever the order of this differential equation is. You've seen already that I've not been afraid to ask you or to give you 9th order, 10th order, and higher differential equations. I have been known to do that. But if I ask you that, if I give you like a 9th or a 10th order differential equation, you can be pretty sure that I'm only going to ask you for the form of the particular solution, because to actually plug in a 9th or 10th order solution would require 9 or 10 derivatives of this. And this, I guess these 3 terms aren't too bad, but this is going to be pretty messy. To take even a couple of derivatives is kind of a pain. Watch what happens when I take some derivatives here, right? So if I take the first derivative now of what I have there, we're going to do that. I actually have to use the product rule here. And I don't exactly care how you group it, but I'm going to make it a product kind of like this, AX and then the e to the 3x. So if you remember your product rule from calculus, we're going to do a little bit of calculus now. I take the first term times the derivative of the second term. So that's going to be 3a x e to the 3x, and then plus the second term times the derivative of the first term, which is a e to the 3x. And then I have to take the derivatives of these other terms as well. The derivative of b is 0, the derivative of cx is c, and the derivative of dx squared is 2dx, like that, okay? And then I have to take another derivative. Thank goodness we only have to take 2 derivatives. It's because it's only second order, right? Now, again, I have to use the product rule here. I'm going to kind of group this as 3ax and then e to the 3x, and I'm going to treat that as a product of 2 things. So we take the first term times the derivative of the second term, and that gives us 9ax e to the 3x. And then the second term times the derivative of the first term is 3a e to the 3x, like so. And then I have to take the derivative of a e to the 3x, which is 3a e to the 3x. And then finally, the derivative of 2dx is just 2d. The derivatives of constants, of course, are 0, which is why some of these terms are disappearing over here. But those are your derivatives. It is going to be helpful to clean this up. 3a e to the 3x and 3a e to the 3x could, of course, be put into a single term. So before I go any further, let me just simplify that into a single term here, guys. So 9a x e to the 3x plus 6a e to the 3x plus 2d. That's what we have. Okay, I'm going to go ahead and mute this table of integrals because in a second I'm going to need more space. Everybody with me so far? Now for the really ugly line, which is where we plug all those derivatives in on the left side. So let's see if I can do this on a Tuesday morning without messing it up. Here's the second derivative. Okay, so now I'm doing the plug in to the differential equation. Okay, so here's the second derivative, 9a x e to the 3x plus 6a e to the 3x plus 2d. All of that is the y double prime. And then I have minus 2 times y prime. I'm going to use some parentheses here to keep this cleaned up a little bit. The y prime is on the board there on the second line, 3a x e to the 3x plus a e to the 3x. All of that is going to have a quantity together. Oh, I'm sorry, I'm not done yet. I still have to add the c and the 2dx there from the y prime line. Everybody see what I'm doing? This is y double prime minus 2 times y prime. And then finally, minus 3 times the original y sub p form at the top of that board there. Ax e to the 3x plus b plus cx plus dx squared. Okay, that's plugging it all in on the left side of my original problem. And of course, this needs to be equal to 28 e to the 3x plus 5x squared. You guys with me? By the way, you'll note, and this is coming from the original problem, right? This is just the right-hand side of the original problem. Okay, so just to be clear, this one is y double prime minus 2 times y prime minus 3 times y, right? That's what we have on the left side. So far, so good? Now, you might notice, guys, that on the right-hand side of the equation, I do not have any term that looks like x e to the 3x over here. There is no such term. So when I see x e to the 3x on the left side, they all must cancel out. And in fact, you can confirm that. You can confirm that. I have 9a x e to the 3x here. I have 6a e to the 3, 6a x e to the 3x being subtracted here. And I have 3a x e to the 3x being subtracted here. These blue terms that I've underlined in blue are all canceling out. And they have to cancel out. We knew that they would have to cancel out because there is no x e to the 3x on the other side of the equation. So that's just kind of confirming that what we would have expected. So this term is gone, this term is gone, and this term is gone. Those are going to cancel on the left side. I don't have to think about those too hard. Where else do I actually have an e to the 3x term? Well, I have right here, this one, and I have this one here. This is 6a e to the 3x minus 2a e to the 3x. That is a total of 4a e to the 3x. I'm going to kind of simplify this a little bit. So these two terms that I just circled give me 4a e to the 3x. And of course, eventually I'm going to match that up with 28 e to the 3x. Probably everybody's figured out what a is equal to already. This guy is going to have to match up with this guy. Okay, so those coefficients would have to agree. I'll come back to that in a second, but let's get the rest of the left side cleaned up a little bit. I have some constant terms. There's a 2d right here, and then there's a minus 2c right here. And then there's also a constant term here, which is a minus 3b. That's just constants. So again, I'll put check marks next to those three terms. Those terms I just put check marks over, I'm just grouping them here. Okay? And then there's also some other terms. There is an x term. Let me put diamonds around the terms that have x's on them. So there's a 2dx, and then here's a cx, but of course there's a negative 3 in front of it. So actually, here's a negative 2 in front of this one. So this is negative 4d and then minus 3c times x. Those are the diamond terms. So I have my check mark terms, I have my diamond terms, and then what are the only remaining terms? Oh, it's just this one. It's just this last one here. So I have a minus 3dx squared at the end there. I'll just do a little cloud around that one. Okay, so I'm just kind of identifying my terms. And so all of that has to equal 28 e to the 3x plus 5x squared. You guys with me? Let's match up the like terms. Here I have 4a e to the 3x, which has to match up with 28 e to the 3x. That tells me that 4a has to equal 28. Just matching up the coefficients on the left side and the right side, yeah. And then the x squared terms have to also match up. So if I match those up, notice that negative 3d should match up with 5. So negative 3d should match up with 5. And then there is also an x term and a constant term on the left side, but there is no such term on the other side. So those coefficients have to be 0. So we have negative 4d minus 3c, that has to be 0. And then we have 2d minus 2c minus 3b, that has to be 0. So here you guys go. We have 4 equations and 4 unknowns. And I did the heavy lifting on this before class to solve for these constants. So I will maybe save you the aggravation of it. You're going to have maybe one homework problem where you have to mess with something that's maybe about the same difficulty. I can clearly see that a is equal to 7. I can clearly see that d is equal to negative 5 over 3. And then using the d value, I can solve for c right here. So it's actually going to end up being, if I didn't make a mistake, c should be 20 divided by 9. So there are actually some fractions here. And then I can figure out what b is by using this last equation and plugging in the c and the d values. And that would be negative 70 over 27. So those are the values. Okay, so we are done with step 2. And now I'm going to actually write down the particular solution with those values plugged in. So with those values plugged in, a was 7, so I have 7x e to the 3x, and then minus 70 divided by 27, again, assuming I did it right, which I think I did, and then plus c times x, that would be 20 divided by 9 times x, and then plus dx squared, which is actually minus 5/3 of x squared. I'm going to put a box around this as well, and that wraps up step 2. And finally, for step 3, guys, I'll just remind you from my lecture last Thursday. On step 3, you're basically just literally, you can see it here, you're just adding the complementary function to the particular solution, which we've already calculated and put into these boxes. If you want, I am okay with you just doing this. You can just not recopy everything again. You can just say y of x equals y sub c of x plus y sub p of x and just call it good. It's just saving you some recopying and rewriting of things. Is everybody okay with this? Are there questions here? Try not to get lost. I'm thinking now in terms of like the exams that are coming up. All of this work over here to solve for these constants, there's not a lot of calculus here. This is mostly just plugging in and then like equating coefficients. It can't be worth spending 20 minutes on it on an exam. You're not going to get that many points for it. If you got A, B, C, or D wrong because you made some algebra mistake here, I'm probably not going to murder you with partial credit loss on that because it's just not, it's not 250B, right? What I want to see is, do you know the 3-step process? Can you do this annihilator method, right? And can you at least get the form of the particular solution correct based on the roots and whether they're repeating or not and whether they're complex or not? That's really where the bulk of the credit would be. Even step 3, just writing this down will be worth something, even if everything is wrong up to that point. So try to be a little bit smart about this in terms of like just when you're taking a test, don't get lost over here too badly into it. Anybody could potentially get one of these wrong by just a silly type of mistake, miscopying a number or a sign error or something like that. It's not worth losing a lot of sleep over that. Okay, so obviously we'd like to get it right, but in the real world, you have more time, you have a computer, you can check your answers and so on. So I don't like to make that a stressful thing for you guys in class either. Questions on this? Feel pretty good about it? Okay, if you're feeling pretty good about it, I'm gonna let you guys practice on a group work here. The first one on the group work, it just says only determine the form of the particular solution. If you try to go solve for those constants, you're gonna be here all day, right? So don't do that, just find the form of the solution and I'll be happy with that. So let's send this around. Just grab a paper and pass it back. And once you've got a handout and once you've got 2 or 3 partners, you guys are welcome to go ahead and find some board space and start working on it. Thank you very much. Let's do it. Yeah. Anyway.
Oh,
If you need to pull up that table of annihilators, feel free to do that. It should be in Canvas.
I gotta watch it.
Guys, here. Come on down, folks. Oh, this is very hot. Just a second. Okay. Excuse me. Everybody has a partner. Awesome. Love it.
But it's like the general.
You guys gonna work together?
Yeah.
All right.
Gotta get
So far, so good. Yeah, let's go. If you can, as long as you don't mess it up.
Right.
Yeah, if you're pretty confident, you need to switch directly to the R's. But I'm okay with that. Yeah, for sure.
But shizzle.
Okay. All right, Andy's off to a good start, it looks like. Great. I love it. That's what I got. Don't forget about the fact that you also have zeros that are that's out in front that does count as one of your roots. There you go. The number of roots that you'll have.
Yeah, but the wise thing you're gonna need to. Oh, you're gonna need wise ones. That's what. He's got the part where those are, no, that's just the white seed you're gonna need to down. This is why you're gonna know what the margins. Oh, yeah.
Yeah, don't forget about the zero root as well. The number of roots that you have. This is by the time you're done, you have 3 roots. Exactly. So see, it's easy to forget about that, but that actually does. That's like your R's out. 0. And then you're gonna get 2. Looks good so far. It's good. It's nice.
The annihilator would go.
For a second, what's the order of these different storage?
Oh, yeah.
It's the third order, right? So that means you must have 3 roots. Right, so it's easy to forget about the fact that I get it out. Otherwise, everything is looking good. Don't forget, you're gonna need the constants front. That's not correct. Dante and Brianna help you. Yes. No, you can put those in any order that you want, and those will be all correct. So good job.
Oh, we just see that.
See what you guys
You
do.
see her, take her.
Imaginary.
Well, but,
What's the mistake? You have a calculator correct.
No, that's just.
You have the new roots correct.
What's wrong with it?
Yeah.
Here it is.
Exactly. You gotta power those up.
So for 0, that just becomes.
Already repeated for the second, third, and before you gotta find them. Yeah. See that? So you always have to go back to zero or any kind of.
Three.
They are. X's, right? That way you do.
E to the.
Sorry?
So we do the.
3x?
Let's see. Remember. Exits right away because trick I use a lot. Yep. It's always familiar when you hear your roots are any of them. And so on this problem, I didn't ask you anything else. You have. That's the only thing I would recommend. That way.
That's just.
You can just. Now you can have that.
Oh, that's yeah.
Everything is. I like it, I like it, great job. Anybody need help, Daniel?
Yeah, like.
How are you guys doing over here? Let's check it. I love the ones that you guys send. Because I love to do this. When I look at my old roots, and my new roots, I see there's some of the same. So this is not the first, second, and third time that I'm seeing zero. This is the second, the third, and the fourth one that I'm seeing. I stack those extras immediately as I start doing. Perfect. You've got, you write down the comment. Okay, just write down the YCC of X, just so from these notes, just so you have it. And then I always like to put it into a box so that if I'm trying to get market credit or whatever. And everything looks great, and all looks great, good job. Okay, did you guys fix this? Ah, you did, this is good, this is good, this is good. Oh, yeah. And X's is some of the new rooms.
I know it's.
That's all perfect, you guys are good under the line. Anybody need help?
Professor.
Yes. Yeah. We do. You won't ever have that. You won't ever have that. It's a theorem. How complex things to a polynomial. That those roots always come in conjugate pairs. So you cannot have a
That's like how-
plus I as a root.
No,
without
it
also has to
And
be.
then.
You have a.
They come as a pair. This is a two
And then now we
for
gotta
two.
find-
Some people like to say, oh, well, is this one the A plus BI and this is the A minus?
It was the general solution.
It doesn't work that way. It's actually two
Particular
thing roots to generate both solutions.
Oh, there.
Happen, you get those roots. I want to think whenever
I
you're
like biology.
dealing with complex roots, they have to be
I don't think it works.
Yeah. Okay, awesome. Let's just double check. Yeah, that's good. Stop. Yep.
I've been using like.
Oh,
Oh, doing back to
I guess fine.
Like
Right now.
Yeah.
Did you write down?
It means we have like a specific set of numbers.
Okay, so
For the most part.
preliminary
I'm not-
function
that's
is
what-
based on these grades. And I'm gonna remind you. You know, you have C1, find
Yeah.
now. Come as a pair, right? And what we talked about last week for that function is that you can make.
Oh, it's just the first part. Back, I don't sit there.
And they are.
That's the thing
No, I like that. But also it's.
So if I write this down.
Right?
It's just this.
That's the only ones I know of.
Okay, and then the next solution is the same thing except for
Oh,
the sign.
I have only gotten through most of the first section. And I think like I'm still.
Yeah.
This is the project.
Together creates.
We have to do a MATLAB script every day.
So it's not like one goes with
Yeah.
this one, no, it's like both of them as a pair. Go with it. Yeah.
Wait, pretty much.
Without one, so it goes over. So you'll always get complex roots two at a time, and you make two solutions. Makes sense? Okay, great. Now the next thing you need to do.
Oh, wait, no, I did it right.
is And then write down.
Yeah, I'm saying.
Try to write down.
I think we're good. Yeah, it's interesting.
Dude, I've been writing on my phone, it's my great like.
Have one mistake.
That's a good thing.
You see what the mistake is? You wanna tell me what it is?
Yeah, we had a
Oh, what's it?
capacitor. Big capacitor.
So notice that your old.
You better not.
And then we had like a double loop one.
And when you went down, I was confused.
Oh.
Actually, so I was- This is not the first size I've seen. It's-
Right now, the site.
Probably do this too, like based off our road, so it'll probably be, if anything, if he is fine. It's me and Jose said on one. Guys in my. It'll be us for it. They're on hospital, so I.
Yeah, no, it's like the first
We'll all
time.
understand the different things and not understand.
Now, this is the second time.
Yes.
That first time.
I already started.
It makes so much more sense.
It makes sense now. Clarity, the posting makes clarity.
You get some TikTok. Obviously, it's on your flag.
This is the mumbo jumbo of the algebra of like. Anybody need a hand?
What?
Snap a hand. Uh-huh.
So when I. You just. Not the whole thing.
You can.
Wait. Just hold on.
You don't have to do that. You just, this is the form.
No, I'm just saying.
You're done with number one. On number two, it doesn't say. They both say find the general solution, but the difference is on number one, they're letting you just stop here. On number two, since it doesn't say you can just find the form, they actually want you on number two to solve for this, go through everything, kind of like I did on the warm-up problem. Yeah, exactly. How are we doing here, guys? Looking good. Number one looks perfect. Now number two.
Doesn't have to be zero. You said even with that, but there's no X here.
Oh.
The Y pizza is zero.
Oh, it would be zero. So this is the annihilator. We get another new root of -3. By the way, this is the how many times it's the third repeat. So this needs to be fixed to x squared, right? We're powering that up already to x squared. And by the way, here you are missing C1. So notice here's your term that doesn't have the x in it. This one does have x. And this one now is already up to x squared. This would be the. No, actually asking to find a higher thing. So you actually are supposed to solve for A now. So. You can take derivative. Look at it on the left side and then match it up with the right side. It's kind of a pain. You have to use that product rule, kind of like on the warm-up prop today. Okay. This is looking super so far, but the preliminary function is good. This is the right form of the particular solution. And now you're doing product rule and try to figure out what A is. It's kind of tedious. It's a lot of work to come up with one number. But at least you can take some comfort that you understand the whole process. It's clear that you understand the whole process. It's just the details here. Okay. So far, so good. Looks good. Anybody need a hand?
We'll have you check our work.
Yeah, I can check. Did you come up with an A value? So your final, is that, of course, using that one.
I'll simplify it.
That's from the one. Oh, it's right here. Right here. Yeah, that looks good. That looks good. That looks good. Beautiful. Guys, oh, wait. You actually don't. You're right. Like you can see that, you know, on the right hand side, I don't have an X squared and I don't have an X. So if I see terms involving square, I can kind of just not even think about it. And if I see terms involving just X, I can kind of just not think about it. So it's really just this one matching with this one, and now that quick. Yeah, I like that short. But you guys feel free to take a 10-minute break.
I did 31. I think I did.
I love it. You guys doing okay?
Yeah.
That looks right. That's the A. That's when you get the A
Oh,
value. That is correct. That actually is correct. That is correct.
What do you mean you already have these from before?
Yeah, I did that one. That's the way we like.
Yeah, so far so
Whenever
good.
you multiply the diameter by both sides.
Yeah.
And then.
Anybody need a hand?
Yeah.
Go about another 2 more minutes, guys, then we're gonna call it good.
Yeah.
This is giving you 0. Yeah. Oh, actually, the couple things. Dude, I use sloppy syrup. Are actually negative. That's okay. So that's a negative. What that does. Oh, that's actually the second time. That's actually the third time that I've seen that rule. So I have to stack and square the and it's gonna make. So this is the form of the. Now solving for A is now. You should actually have to use the bottom. It's not gonna give you that time. You can look at my solution. It's just a matter of taking the 2 derivatives of this, plugging it into my website, and then you'll solve it. And it's definitely not. But looks good. Looks good. Looks good. Oh, that's it. Minus. That is the right number. Guys, when you're finished, you can take a 10-minute break. We're gonna take a 10-minute break right now. Feel free to do that. Is there any? 2 is right. That is the right number. Good job. I love it. I love it. Can I jump in here? On the right hand side, I don't have any X squareds and I don't have any X. Just get rid of all of it. I don't even need to do it. You got it. Bang, bang, bang. 2A has to equal. You got it. You got it. You got it. You got it. So this becomes a 2 right here. And that's your answer. That's it.
And then this.
That's that.
Let's say general solution.
And then you can do the step 3. We're gonna get into the habit of that. Writing down what the y of x is. Guys, if you need a little stretch break, feel free to step outside and do that. If you need any help on the homework for tonight, we can make a little space over here. Yeah, this is 8.3. And I'll try to save a few minutes for that as well. All right. A little short break. Good job, guys.
What?
Did it ask us to solve for the form of 30?
30 is just asking for the form of YP. specs.
It's asking you to do like what we did for 28.
You don't have to solve for the constants. You basically have to do everything else. Then.
But you can't like back. Fluids drag us.
Grab your trivial solutions, the annihilator table, I think you do. That's 30.
For 30? Oh, you still got 30? For 30, you have to do general. Sorry. I thought you were talking about the next one.
Next one.
42 and 43. Just solve for YP. I think. I looked it up and that's what.
You're not solving a conflict at a rise on sure. Yeah. Which one should be preventable? 42, 43.
I don't know. I don't think this will be terrible. I'm doing it right now.
But she's gonna do it.
Yeah, you might as well put it on. I would like to see him do maybe 30.
Oh, you'd like
Actually, no, I think I get 30. Maybe 28.
but it's purple, so I don't know.
Oh yeah, I want to see him do 30 because there's a factor where it's DQ. I don't know how to factor that. I can give you the factored form because I don't know how to do it. Like it turns it's this.
I'm just trying to do it.
Yeah. I don't know how to do
it. But he removes 2 quizzes at the end. So technically,
I always forget my C1s.
So you
Here's the factor. Professor, for 30, how do you factor? Yes, I looked up the factored form.
Yeah, whenever you have a polynomial like that and you're looking for rational roots, by rational roots, I mean things that are whole numbers or fractions,
Okay.
which is what 99.999% of them would be on a 250B type of an assignment. The rational roots always have to be divisors of the constant term,
Ooh,
which means that
it can only be
1, 2, 3, 6, and -1, -2, -3, -6.
so test it.
You have to just test.
That's what my thing's talking
One,
about.
if you manage to find one, then you can do long division to find the other one. Long division of
I was
polynomials.
asking AI. I said to do synthetic division. I was like, oh.
Synthetic division or long division of polynomials, whatever you prefer. But yeah, that's unfortunately, that's how it works.
Would you give us that on an exam?
I wouldn't be very happy with that kind of a question because then people will be struggling with the problem for the wrong reason. Because I'm not really interested in seeing people factor cubic equations. That's not what MATS-CPB is about.
Okay.
But you know, it could happen, but yeah, it'd be I was like desperate for a problem. Something like that.
Long division polynomial. So fun.
It would be like.
Obviously, you want to show up. Yeah, no, definitely. Yeah.
Wait, what?
Yeah, because I had a.
Oh.
Because your moving is using. But it's like. Well, it depends.
Just to.
But he did where. He gives you like, well, at least for us, he gave us. To solve it, and you just gotta like, think that you're when it comes down. Yeah, so it should be.
It's supposed to rain again today, so.
But that,
Is it supposed to rain again today?
I think the weather was. Thought it was.
What's that?
Thought it was.
It does.
End up looking over.
It's fine.
I get 50-50 chance, bro.
This whole week's gonna be kind of wet.
I checked this.
Oh, wait, what?
All right, guys, I think I'm gonna go ahead and get back started again here. So maybe one person's still outside, but I see a little list of problems. It's getting longer by the minute. I'll see what I have time for. You know, each of those takes a little bit of time. So if I don't get all of those problems answered and you still have questions, what are you gonna do? Office hours. Stop by my office hours. Exactly. I have office hours right after class, and I also have office hours tonight. So the one thing you shouldn't do is just blow it off and like not really get your questions answered, because ultimately that usually means that you're not quite where you want to be with the material yet. So I would definitely, I'll do what I can to answer at least a little bit of that list, but that's like most of the assignment actually. So I'm not sure I'll really have time to go over most of that. Instead, what I want to start with right now, guys, is the example that I've put on the board here in front of you. And I'd like to just play along with trying to solve this one. And we're going to see when we get into it that there's a little bit of a problem here. Okay, so let's take a look at trying to solve this. Remember that we have our three-step process. So this is it, y double prime minus 12y prime plus 36y equals e to the 6x all divided by 1 plus x squared. Okay, so as you guys know, step one is to write down the auxiliary equation. And some of you have been going directly to the auxiliary equation without even doing the D notation first. That's okay with me. If you can just look at it and tell right away how to turn the D's into R's, that's okay. You just have to make sure you do it carefully because it's important to get these roots correct. My auxiliary equation here looks like it should be r squared minus 12r plus 36. This actually factors very easily as r minus 6 quantity squared. And so my roots are 6 and 6, and these are what we would call the old roots in step one. Okay? So far, so good. The complementary function, therefore, does somebody want to tell me what it would be?
C1.
The actual, let's just go straight to the whole complementary function. Actually, let me hear from somebody I haven't heard from in a while. Max, do you want to tell me what the complementary function would be based on those roots?
C1.
Okay.
C2. X.
Nice. We have stacked this x here because there was a repeated root of 6, and so we have the terms looking like that. So far, no problem. So far, no problem. Now, let's talk about step 2. Step 2 is where we have to come up with an annihilator. And so at this point, I'm going to get out my red pen. Red pen means what I'm about to write down is not good. It's not correct. We don't want to see the red pen. When I look at this annihilator, I always, every semester, somebody will do this. They will say, oh, the annihilator of e to the 6x, that's just d minus 6. And then they'll say, oh, and the annihilator of 1 plus x squared would be, a d, and then, or a d cubed, and they'll do something like a plus here, something like that. This makes no sense whatsoever. You cannot divide by the d operator. Like, I wouldn't even know what this means, right? So I wrote this on somebody's paper once and they started crying. This is absolutely, it doesn't even make sense. Like, it's like, I wouldn't even know, like, if you put this in front of me and said, do this, I'd be like, do what? I don't even know how to do that. I can't really divide by a d operator. Okay, so this is not the correct annihilator, right, for the a of d. So yeah, I was trying to write down an a of d, but that didn't work. So I can go to my table. I've got my table up here. Does anybody see anything that's going to help me to annihilate e to the 6x divided by 1 plus x squared? I know how to annihilate powers of x. I know how to annihilate exponentials. I've got sines and cosines here. Do I have any fractions there?
Nope.
I don't think so. I don't think so. This is a fraction, guys. This capital F of x is a fraction. And when I think about annihilating it by using derivatives, what I'm really suggesting is that we would have to use like the quotient rule to start taking derivatives of this. And usually when I use the quotient rule, my expressions, they just get messier. They get more complicated. They don't ever go to 0 or anything like that. So I'm really in a pickle here, guys. This step 2 is suddenly a problem for me. If my f of x isn't just powers of x or sines and cosines or exponentials all upstairs, I don't have it in my table. And what we're now talking about is a shortfall, a shortcoming of the annihilator approach. The shortcoming is that we can only use that annihilator approach on things that we have annihilators for, right? And we don't have an annihilator for this right-hand side. There is no annihilator. There is no annihilator a of d for this capital F of x, which, as we just said, it's e to the 6x over 1 plus x squared. There is no annihilator for that. So we need another approach. When we don't have an annihilator, we need another approach. And that other approach, so we need a new approach. And this is only for step 2. So step 1 is fine. Step 1 is absolutely fine. But we need a new approach for step 2. And I'm going to teach you a new approach right now, guys. It is in section 8.7. It is something called variation of parameters. It is called variation of parameters. And in order to really explain this variation of parameters approach, I want to come back for a minute to this complementary function that we wrote down in step 1. We are going to need to sort of pick out the 2 individual solutions that were used to build this complementary function. So the first solution, you can see it right here, is simply e to the 6x. I'm going to call that y1 of x. And then y2 of x was the one where we stacked the x on it. So it's x times e to the 6x. These are the two individual so-called basis solutions for the associated homogeneous differential equation. And we're going to be referring to those when I explain this variation of parameters method. Okay, so this is going to be a bailout. This is gonna be when you don't know how to annihilate the capital F of X, here's another way to do step 2. Okay, if we don't have it in our table and we're looking, oh, how do we do step 2? It's called variation of parameters. However, I'm going to make your life a little bit easier in this section because you can do variation of parameters for any order differential equation, but it's almost impossible to do it by hand if the order of the differential equation is higher than 2. So we are only going to explain this for second order differential equations only. It's not that you cannot use it for higher order equations, but you would almost certainly use a computer at that point. I'm not going to be having us use computers in this class, so we're only going to explain it for second order, which actually is good enough. You'll get the idea of how this method works, and then in the real world, if you're ever faced with a higher order equation where you don't know how to annihilate the right-hand side, then you'll be able to generalize this, and it's the same approach, okay? So we're only going to do this for second order, guys. So if you see on the next exam, if you see a third, fourth, fifth, sixth, whatever order differential equation, you're not going to do this, right? This is only for second order. Okay. And how does this work? Well, I need to explain it. The idea here is we're getting used to doing this. We will guess a trial solution. There are going to be a couple of equations here, guys, that we have to memorize in this section. And so I'm going to give you the first of those right now. So there's a trial solution for y sub p. And what we're going to do is we're going to call it u1 of x times y1 of x plus u2 of x times y2 of x. I'm going to put a box around this. Okay, and this is going to be where u1 of x and comma u2 of x are to be determined. So I have to explain what this u1 and this u2 is in just a second. I'm going to have to explain that. One thing I can already explain is why it's called variation of parameters. If we go back to the complementary function over here that we wrote down in the box here, what's really in this box, my friends, is the complementary function c1 times y1 of x plus c2 times y2 of x. Remember that I'm using the y1 and the y2 as the two basis solutions here. So if I just use that notation, this is C1, Y1 plus C2, Y2 is step 1. So what I'm doing in step 2, guys, is I am varying the parameters. The parameters are C1 and C2. And I'm going to take a trial solution, a guess, again, somebody way smarter than me and way before I came along, figured out that this trial solution is going to be the magic ticket that works. But we are changing C1 to U1, and we are changing C2 to U2. The C1 and the C2 were constants. They are parameters that are constant values, and we are going to allow them to vary as functions of x now. U1 and U2 are actually going to be functions of x that vary. Okay, turns out that this guess will work. This trial solution will work as a bailout on step 2 as long as we choose U1 and U2 correctly. And I'm going to tell you what the U1 and the U2 are. Actually, the way you figure them out is you take this trial solution and you stick it back in on your differential equation. On the left side, on the right side, you match everything up and you figure out, well, what does U1 and U2 have to be? It's the usual way that you take a guess and you tweak it, you refine it, you figure out what its individual parameters are in order to make it work correctly. So I used to spend 30 minutes in this class, like deriving U1 and U2. And I kind of got tired of that. So I've got the Canvas page up here with the special handouts again. There is a document near the bottom called Variation of Parameters. In this document, I'm going to go ahead and open this one up. Let's see if I can actually make it a little bit bigger here. In this document, I actually do a derivation for this thing. So let's take a quick break from taking any notes here. I'm not going to ask you to like remember this in detail, but just so you know, you've got your differential equation here. Notice it's second order only. Y double prime plus something times y prime plus something times y equals f of x. That's the original problem. And we go through and we find the complementary function. C1 times y1 plus C2 times y2 is exactly what I was just talking about over here. Okay. And then at the bottom of my slide there, I'm going to scroll this down just a little bit here. We take this trial solution. So what I just wrote down, y sub p equals u1 times y1 plus u2 times y2. That's what I wrote on the board here. U1 times y1 plus u2 times y2. And what did I say here? We must substitute it into our differential equation to solve for u1 and u2. Okay? So you do that. You have to take a couple of derivatives. So you start with u1 times y1 plus u2 times y2, and you just use the product rule to take the derivative of that. U1 times y1 prime plus u1 prime times y1. And then u2 times y2 prime plus u2 prime times y2. That's just the product rule. Now, when I go to the second derivative, this is only the first derivative. I, of course, have to take two derivatives because it is second order. When I go to the second derivative, we would actually be using the product rule 4 different times, ending up with 8 different terms. Turns out that's a little bit more than we want to deal with. So somebody, again, way smarter than me, figured out that we can maybe make this a little bit easier if we just simplify. See if I can get both of these up here. Out of these 4 terms, we're just going to assume that the second and fourth term, if we could possibly make them equal to 0. Now, we might, again, we don't have a good reason for doing that. We also might have just screwed ourselves out of being able to solve for u1 and u2 by making this assumption. But it turns out that if you make that assumption, then instead of 4 terms here on the right side of the derivative, you only have 2. And so if you then take the derivative of y sub p prime to get the second derivative, instead of 8 terms, you would only get 4 terms, right? So the first derivative would only have 2 of those 4 terms left, and the second derivative would then only have 4 terms. As usual, you take this whole thing, you plug it back into the original differential equation, and it turns out, I'm going to skip some of the messy algebra here. It turns out that your equation, remember, we're trying to solve for u1 and u2. We're on this to be determined part right now. What are u1 and u2? Well, it turns out there's another equation involving u1 and u2, which is, it would be this one right here. I'll let you guys stew on that a little bit. I won't go into all of those details, but the 2 equations that we had, there was the one that was sort of that cheating assumption that we made, which is equation A up here at the top, this one right here that I'm highlighting, along with the one that we can derive right here. It can be put into this matrix as a single matrix equation where the u1 prime and the u2 prime are sitting in this column. The matrix on the left has y1 and y2, and then y1 prime and y2 prime. And the right-hand side is 0 and f. You can just put those 2 equations into a 2x2 matrix system. And the goal is to solve for u1 and u2, right? We're almost there. All I have to do to solve for u1 and u2 right now is take an inverse of this matrix. And then obviously, eventually, we're going to have to do an integral. I hope everybody's ready for some integration. There will be a little bit here. But essentially, it's a 2 by 2 matrix. We can invert it. Oh, there's the W thing. Oh, do you guys remember the inverse of a 2 by 2 matrix? We're gonna need to know this again. This goes way back to chapter 2. You take the 1 over AD minus BC, right? That's actually just the determinant of the matrix. And then if you remember, you swap the diagonal values, and then you leave the other two in the same places, but you change their sign. That's actually what happened here. Notice that there's minus signs on these off diagonal values. The y1 and the y2 prime switched places. And the determinant, do you guys remember the determinant of this matrix here? The determinant of this matrix is called the, say it again? The Wronskian. It's the good old friend W that we learned about not that long ago. The Wronskian. So we see that show up right here. 1 over the determinant is 1 over the Wronskian. Here's the rest of that inverse matrix. Here's my 0 and F. And if you just do your matrix multiplication of this matrix times this vector, you create these two equations for the derivatives of U1 and U2. Last step is simply to integrate both sides. So I'm just going to say in the notes now, see handout. If you really want to see all those details, I did it in 5 minutes. I used to spend 30 minutes doing all that. I just wanted to go quickly through it. But the handout has all of those details in it. But here's what you really need to know. And if you just need to memorize these, go for it, okay? Here are the formulas. U1 is negative the integral of y2 times capital F divided by the Wronskian. You can see that here, right? U1 is negative the integral of y2 times F over W. And U2 is positive the integral of y1 times F all divided by the Wronskian. So there you go. Those are the formulas. The way I remember these formulas is the subscripts of the U's and the Y's are flip-flopped. U1 involves Y2, U2 involves Y1. They both have F on top and W on the bottom. And you have to integrate. That's it. This is a pretty easy section. Let me just mute my screen for a moment. I'm going to want to pull it back up in a minute, but let's see if I can get it back on in a second. If you guys memorize these equations in these boxes, there's nothing else about this that's very difficult. Of course, you'll have to do integration, but that's not really 250B, so I don't worry about that. The rest of it is just totally straightforward. Let's go back to our example and try to finish it now. Back to the example.
Thank you.
Back to our example. So what is, actually what I like to do first is my W. I like to calculate the Wronskian first. So the W is the Wronskian of Y1 and Y2. So this is a determinant of a 2 by 2 matrix. Now, how does this matrix get put together again? We lay our original functions onto the first row of this Wronskian matrix. So this would be e to the 6x, and then x e to the 6x. And then on the second row, we take the derivatives of those. So the derivative of e to the 6x would be 6 times e to the 6x. And for the derivative on the second column, I actually have to use the product rule. So the first term times the derivative of the second is actually 6x e to the 6x. And then plus the second term times the derivative of the first actually just gives me e to the 6x again. So this is my determinant. And I'm actually going to work this out as my little, it's a little 2 by 2 determinant, yeah, that I have to calculate. So how does that work? I do AD minus BC on my little 2 by 2. So we'll have e to the 6x and then times 6x e to the 6x plus e to the 6x. And then minus x e to the 6x times 6e to the 6x. Let's say that 3 times fast. It's a lot of word twisting you have to do to spell all that out, but that's actually what you have. Now, guys, this first term right here that I underlined is literally identical to what ends up getting subtracted later. So the underlined part, if I FOIL this out, this underlined part actually cancels the subtracted part. And the only thing that survives is actually the part that I didn't underline here, e to the 6x, which is being still multiplied by e to the 6x. Guys, that turns into e to the 12x. If I'm going too fast, please slow me down. It's the algebra here, and I don't want anybody being lost on this. So e to the 6x times e to the 6x is e to the 12x. This is my Wronski. I like to just calculate this first before I plug them into the U1 and the U2 that we're going to do next. Okay? All right, let's try and, is everybody okay? The Wronski? That's the W part. That's going to go in the denominator of both of these integrals. So let's start working on the U1 and the U2. U1 is negative the integral of, and I'm going to have a fraction here. In the denominator, we can go ahead right now and put our Wronskian in there that we just calculated. That's e to the 12x. Ultimately, this will be integrated with respect to x. By the way, what goes in the numerator? I have already put my minus there, but on top I have to have y2 times f. So y2 is coming from step 1, and the f is whatever was up here in the original right-hand side. So the y2 is x e to the 6x. That's y2. And the f is e to the 6x, and then it's divided by, so I'll put it in the bottom, divided by 1 plus x squared. Hold this a little closer here. Yeah. And, well, this has been rigged to be really nice. The e to the 6x and the e to the 6x actually cancels the e to the 12x that was on the bottom. And the only thing you're really left to do here, guys, is negative the integral of x over 1 plus x squared dx. And it's been a little while since we've had to do a u substitution around here, but we are in that position right now. If I make the denominator into like a u, I'm thinking of u substitution from calculus, the derivative of 1 plus x squared would be 2x dx. So I can put a 2 there at the price of a 1/2 out in front if I want to, or I can just do it in my head. You end up getting negative 1/2 of the integral of du over u. And the integral of du over u, guys, is the natural log of u. So you end up with an ln of 1 plus x squared. Normally, when you do an indefinite integral, you have to add a plus c on the end of it. This is typically what they hammer at you in calculus. However, remember, guys, in step 2 of our 3-step process, we only need to find one particular solution. So I don't have to figure out like a general antiderivative here. I can just choose my plus c to be 0. So we don't even have to write it down in this case. We can just leave it as such. Does that look okay? That's U1. That's U1. Let's write down U2 as well. So this is U1 right here. Got that one done. Let's go figure out the U2 value. I think I'll erase my Wronskian calculation here so I have a little bit more room. I'll just do it right here. And again, really the main thing is you just have to learn these formulas. And you'll be good to go in this section. U2 is the integral of y1 times f over w. Let's put the w on the bottom first. That's e to the 12x. And then y1 was just e to the 6x, so that goes on top. And then the capital F is e to the 6x, and it's divided by 1 plus x squared, which actually technically we could put downstairs again. There is no minus sign on the U2 formula. If you go back to that derivation on the handout, you'll see that you don't need a minus sign here. But again, the exponentials all cancel. And you're left with just the integral of 1 over 1 plus x squared dx. Does that integral look familiar to anybody from calculus? It's almost a tangent. It's the inverse tangent, the arc tangent, whichever way you want to say it. Yeah, this is the arc tangent of x. It's also in the table of integrals on your cheat sheet that you'll have, so you don't have to memorize that one either. So that is the U2 value. Okay, so we have U1 and now we have U2 as well. And so I can now write down my particular solution by just plugging everything in. Let's just do that. Y sub p of x would be U1 times Y1. So U1 was negative 1/2 of the ln of the quantity 1 plus x squared times Y1, which was e to the 6x, and then plus U2, which is the arc tangent of x, times Y2, which was x e to the 6x. We'll go ahead and put a box on that one as well. That's step 2. So we have bailed ourselves out. We didn't have any annihilator to use, so we bailed ourselves out and just wrote down a guess. The guess was U1 times Y1 plus U2 times Y2, this thing right here. Okay? So what do you need to take away from this little lecture so far? You really just need to know when to use this method. You're only going to use it on a second order differential equation, and probably only if you don't know how to annihilate capital F. If you can do the annihilator method, most people like that pretty well. But if you don't know how to annihilate capital F, and it's only second order, then this is the method you're going to use. All you really need to remember is the formulas for the particular solution, as well as the U1 and the U2 that show up in those formulas. Really cookbook, it's really computational, not a lot of heavy concept here. This is just kind of plug and chug, plug and chug. Yeah. Questions at all? Yeah, Jakob.
So in this case, since we don't have an annihilator, it's not going to form the YP of x. It just goes straight into the YP of x, right?
Because there's no annihilator, we can't even think about that approach. We're kind of totally pivoting to something new here, which is let's take a different stab at how to get step 2 done. Step 1 is the same, and step 3, did I do step 3? Oh God, forgot step 3. Step 3 is the same, right? So step 3, I'm gonna put it right here, guys. Step 3, this is just where you write y of x equals y sub c of x plus y sub p of x. I won't take 5 minutes to recopy the whole darn thing down again, but you're basically adding this one here, which was step 1, to this one here, which was step 2, to get step 3. And you're welcome to just abbreviate that third step like so. Okay? Yeah, so it's only step 2 that is changing. Steps 1 and 3 are the same as before, and even step 2 isn't that bad if you know these formulas. Okay, so there's going to be some homework on this for Friday. I think I've got maybe 2 of these for you guys to practice, and I think on Thursday in class I'm going to do some group work to just practice this a little bit. Can I pull this screen back down again, or is anybody still copying over here? I'll wait just a second. Let me turn on my screen. Some of you might be wondering. Oh, sorry. Some people are still trying to copy that down. I can't turn it off. All right, you guys just have to wait a second. If you're not done copying, just have to wait a second. It's not as fast as I thought it would do. Some of you might be wondering, wait a minute, we did section 8.1, then we did 8.2, then we did 8.3, and now suddenly I jumped to section 8.7. I'm sure you guys are all dying to know, what is sections 8.4, 5, and 6? Yeah, well, that's the stuff that your other professors have to teach you. I'm just here to teach you the math, right? I get away with just that part of it. But there's a few sections in the middle of chapter 8 where we actually find out what this stuff is good for. Like, when do these differential equations come up in the real world? I am sure you're going to see it, not just in the real world, but as soon as you go over into your 300 and 400 level engineering classes, they are for sure going to be showing you these applications. And I even had a student on one of my SOQ forums several years ago. They said, it'd be really nice if you could just take a couple minutes to like give us a preview of where this is actually going to come up in our engineering classes or in the real world. So you know what? I took that advice to heart. And let me go back to this special handouts folder one more time. In here, I actually made a little handout. I'm going to download that as well so I can blow it up a little bit. It's another one of these handwritten things. And again, guys, you don't really need to take notes on this because this is not what I'm going to be focusing on for this class. But engineering applications of these higher order differential equations, like what is this stuff good for and when does it really come up? I put two examples onto this handout, kind of cut the paper in half here. The first one is oscillations of a mechanical system. So if you have a spring that is bouncing on a, through the air, on the end of a spring, you have some mass here. And you would like to figure out what the position of the mass is as a function of time. That would be y of t that you would like to solve for, right? That's the position as a function of time. Well, there's a differential equation that governs the free oscillations of this mass. And it involves some constants here. You can see there's a K. K is just the spring constant, so that the stiffness of your spring that the spring is kind of bouncing on, that's kind of a factor that you have to include. There's also a C value. This would be some kind of a damping effect, like maybe there's some air resistance as this mass is oscillating up and down that kind of affects the motion of the mass. So C is again another constant that you might have to think about. And then M is the mass itself. How heavy is this object that is on the spring? So you have all of those things that kind of show up in your differential equation. And what do you have, guys? You have a second order linear homogeneous differential equation. And so you can solve for the roots of the auxiliary equation. Of course, those roots will be in terms of those constants, the C and the K and the M. They're all going to be part of it. And you can solve for those roots. And depending on what those constants are, you might have two complex conjugate roots. Okay, that's where you get sines and cosines. You get all these oscillations, right? Or you might get one real repeated root. So you could get a single repeated root. This is called a critically damped system. And so you can see kind of what the behavior of the mass would be in that case. Not so much oscillations. It's more like just dying off, right? And then this is what's called overdamped cases when you get two distinct real roots. And again, the solution kind of passes through this equilibrium at most once. This is an extremely stiff spring. Like you pull the spring down and it is so stiff, it just kind of basically bounces right back up to the equilibrium position and stops. It doesn't do any oscillating like it does in case one, right? So you can look at all three of these cases. I'm sure if you're going to take a mechanics course in your engineering department, you will definitely talk about this, and you're going to see these second order differential equations there. And now you kind of know where it's all coming from. We just do this whole auxiliary equation business and we look at the roots, what kind of roots we have. So it's kind of a nice application. On the bottom half of the handout, I did a similar analysis with a circuit problem. Oops. So let's scroll this down just a little bit. Again, I'm just blowing by this really fast. You're not supposed to like completely absorb everything. This is not going to be on your exam. I just want you to like see that, yes, this stuff is actually important. So if I take a circuit that's got some kind of a battery source over here, which is E, electromotive force, and I've got a resistor and a capacitor and an inductor on my little circuit here. This is called an RLC circuit. The main question here is, what is the charge as a function of time? Charge is denoted with Q. What is that charge as a function of time? That's the unknown function. that is in this differential equation. And again, you get a second order differential equation. This one is not homogeneous. So there's something on the right-hand side. So you'd have to do the three-step process, right? Solve the complementary function, find one particular solution, and then add them together. You'd have to do all of that. But it's a very similar second order non-homogeneous equation. I kind of pooped out on like working out all the cases again. I just sort of wrote down, okay, so you could actually do the math on this and figure out the nature of the solutions based on what kind of roots you came up with. So I just left that kind of brief. But just so you know, sections 8.4, 8.5, and 8.6 of the book go into these applications in more detail, right? So you'll see the actual problems there where you're doing the real world applications of this stuff that we've been learning. But they pay me to show you guys the math part, and then your engineering professors then get to show you the application part. But hopefully, if I'm doing my job well, then when you go take those engineering courses, you can focus on the engineering aspects of it, and the math part, which is kind of in the background. Hopefully you'll already feel pretty comfortable with it. That's my goal anyway. And do my best with that. But that's kind of the way the engineering department likes to do things. They send you over here to me to learn the math part, and then they get to teach you the real world engineering applications. But I did get a recommendation to just at least make a handout on that. You'll find it in the Canvas folder, so feel free to stare at that a little bit more if you want to. Special handouts folder, we've been giving that link a workout lately. Is everybody so far so good? Can I show you one more application side of things before we go any further? We're not going to get too far into this, but I'm going to do one more application idea, and then we'll try to save a couple minutes to look at a couple of those homework problems. What if we had this problem? What if we had a linear system of differential equations? Do you guys remember back at the very beginning of the semester? I want to give you another real world example. Do you remember way back? This was like the very first week of the semester back in August when it actually didn't get dark at 5 o'clock. And we had like some solution of chemical in here. And there was some amount of chemical as a function of time. And you might remember that we were pouring some chemicals into this tank at a certain rate, which I think I called R1. And then there was a concentration C1. Feels like it's just yesterday, doesn't it? And then there was also a leak out of the bottom of this tank. And so you had stuff coming out of the bottom at a certain rate, R2. And there was a certain concentration coming out at a concentration of C2. Do you remember this? Yeah. And there was a differential equation for this even. It was something like dA dt plus R2 over V times A equals R1 times C1. There was this differential equation. This was way back before we did any linear algebra at all. And we learned that we can solve this as a first order linear differential equation. But I want to throw a little wrench in this now. What if there was a second tank right next to it? And in this tank, there's also a certain solution that is an unknown function of time. I'm going to call this one B of t. But again, we are pouring stuff in at a rate, I'm going to call it R1 prime and C1 prime. And again, there's chemical leaking out, maybe at a rate of R2 prime and C2 prime. These are just 4 different numbers from the 4 numbers on the first picture. And this would be another first order real world problem that we could solve, except that I'm going to make this more interesting by creating a pipe between the two, where the chemical can actually be flowing from left to right and from right to left, which actually means that how much chemical is in A of T affects B of T, and B of T affects A of T, because they're all basically connected together. So you could pour a ton of salt into the A of T side, and this side might just be filled with water initially. But after a certain amount of time, because the two tanks are hooked up now, right, the salt that was over here is going to flow to the second tank. And so B of T is not just going to be zero forever, it's going to start to accumulate salt from the other tank. And actually, in this system of tanks, we have more than one unknown function. We actually have two. We have A of T and we have B of T. Guys, most real world problems involve more than one unknown function. There's rarely a problem that I ever solve where there's only one unknown function. Usually there's lots of parameters. There's lots of things that we don't know that are somehow interconnected to each other. And so we haven't looked in this class so far at any differential equation where there was more than just one unknown function. It was always y of x that we were solving for. But what if there was, you know, an A of T and a B of T? And we would like to know both of those unknown functions of time, right? We actually get what is called a linear system of differential equations. And so the goal here is going to be to learn how to solve linear systems of differential equations. And this is actually the start of the last chapter of this class that we're going to cover. There's actually 11 chapters in the book, but we're going to be running out of time with chapter 9. So I just give you here a little motivation that we would like to be able to solve this kind of a problem too, where there's more than one unknown function. These unknown functions are going to be linked together in what is called a system of differential equations. And on Thursday, because it's a system of equations, on Thursday, the matrices are coming back. The vectors are coming back. We're going to see eigenvalues. We're going to see eigenvectors. We're going to be doing null spaces. We're going to be doing determinants. It's all going to be a part. This is the climax of Math 250B. One of the reasons I love teaching this class, my friends, is that the best part of the whole class is right at the end when we put it all together. So I'm going to contain my excitement for now. I have to save my energy for 48 hours. But on Thursday, get ready. We are going to start into chapter 9. Okay. What I'd like to do with the 3 minutes that I think that clock is wrong, actually. Yeah, I guess I have 4 minutes. I'm going to take just a minute to look at the homework problems that are on the board over here. And I'm going to have to be pretty picky and selective, and I'm not going to necessarily solve them all the way out. So let me just give you a few little hints, and then anything else we'll have to just wait for office hours, which is totally okay. The main thing, guys, is just please don't just blow off the homework. If we can't get it all done right now, I'm happy to help you later on if you need it, okay? The main thing is you need to learn this stuff. Let me say a quick comment about number 30. This is from the homework that's due tonight. Here is the equation that you're solving. I'm going to write it down. Y triple prime plus 2y double prime minus 5y prime minus 6y equals 4x squared. The thing about this problem that is tricky is when you write down the auxiliary equation. So on the left side, we can quickly write down r cubed plus 2r squared minus 5r minus 6 equals 0. The thing that makes this one a little tricky is just factoring it. So people get stuck on number 30 primarily right here because you have a cubic equation and you're like, what are the roots? How do you get them? We don't have a nice formula for it. It's not obvious how to factor this. But here is the idea, guys. The candidates for the roots. Remember that for a cubic equation, you only have 3 roots for a third degree equation. The candidates for the roots, guys, you might have learned this in high school. It's called the rational roots test. The candidates for the roots are just the divisors of the constant term. So you think about what numbers divide 6, and you've got 1, 2, 3, or 6. And you also have to take the negatives of those because minus signs don't really affect divisibility at all. There's actually 8 different candidates. These are candidates for the roots. Remember, only 3 of them could possibly be the roots. But what you can do when you have a little list of potential roots like this is just plug them in and just see. So if I plug in 1, I get 1 plus 2 minus 5 minus 6. Well, that doesn't work. But if I plug in -1, I get -1 plus 2 plus 5 minus 6. That actually works. This is one of your roots. Okay. And now you can just try the other roots. You could also do long division, and like once you know that r minus 1 is a root, you could divide by r plus 1 here and get some quadratic quotient. Once it's factored with a quadratic, you'd be able to get the other 2 roots much faster. Okay. Or you can just run through all these candidates and find them. Okay, so that's my little hint on number 30. The rest of number 30 is pretty straightforward. This is the part that usually throws people off. Let me quickly look at, maybe I'll do 42. I see 42 and 43 over there. I'll mention something about 42 because it's an even numbered problem, which isn't going to be having an answer in the back. And then this is probably all I'm going to have time for today, guys, just these 2 quick problems here. But on 42, they give you d squared plus 4 times d minus 2 cubed of y equals 4x plus 9x e to the 2x. And the important thing on 42 and 43, these are the last problems on the assignment, is it only asks you to find the form of the trial solution. It says do not solve for the constants that are in the trial solution. So this actually makes your life easier. You don't have to solve for the A, B, C, D, whatever letters you have. You do have to do step 1, right? So you start off with the auxiliary equation here. So this is step 1. And did I copy this thing? Yeah, that's right. And so you can quickly figure out the roots. You've got plus or minus 2i coming from the first factor. And then r minus 2 cubed gives you the roots 2, 2, and 2. Be sure to write down the repeats so that you remember to stack those x's. This is 5 roots, guys. And so you're going to create a complementary function that has 5 terms. Okay, so let me write it down really quickly here. For these imaginary roots, we use sines and cosines, right? So you're going to get like C1 times the cosine of 2x. If you're wondering where the exponential is here, because there's no real number in front of the plus or minus, there's no e to the ax part. You can kind of just ignore that. And you're focusing just on the sine and cosine. All right, so this is C2. And then the rest of these terms are just C3 e to the 2x. C4, we have to stack an x on that, e to the 2x. And then C5, x squared, e to the 2x. So far, so good? That's the first step. To get the second step, again, I'm just going to very quickly do this because I've only got like a minute left. The annihilator for the right-hand side consists of 2 parts. What's the annihilator of 4x going to be?
G squared.
D squared, two derivatives, right, would take care of that. And I'm going to multiply that by the annihilator of x e to the 2x. Remember, the 9 doesn't matter. X e to the 2x. I will save you the headache of that for right now. It's actually just d minus 2 squared. You can get that from the table, right? And so my new roots here, guys, just really quick, the new roots are just the roots of this, which is 0, 0, 2, and 2. Yeah? 0, 0, 2, and 2, and the 2's are actually repeated already. So let's just get the form of the particular solution and then we'll call it a day. I've got my 2 zeros that are appearing for the first time down here. So I have an A and then a BX. I stack that X because the 0 is showing up for a second time. On the 2's, I have to recognize that the 2's are now showing up for the 4th and 5th times because we already saw 3 2's earlier. So this is the 4th and 5th time. So on these next terms, I'm going to have to really jack up my x's. Cx cubed e to the 2x, and then dx to the 4th e to the 2x. This would be the form of the particular solution on this problem. And you do not have to solve for A, B, C, or D on 42 or on 43. Okay. I know that was a little quick. Unfortunately, it's probably all I got time for right now. Any questions though on either of these two that I just kind of gave a quick run by on? If not, guys, let me let you go. I will see you on Thursday or in my office hours, whichever comes first. Bye for now. Take care.